Right, so first, I just want to thank Patrick for inviting me to give a talk at the seminar. So today I will talk about my recent work, soft-strong unit solution for a robust recovery. This is based on the joint work with Jala Fadili and my former PhD student. The paper is available on the archive already. Oh, by the way, I just wondering how much time do we have?
I would say 40, 45, 50 minutes, up to you. How long time do you think you need?
Okay, I think I will try to make it like 45 or 50 minutes. Okay. Sorry. Okay, so here's the outline of my talk. First, I will recall some information about robust recovery, and then the role of soft-strong and unit solution for robust recovery. And then I will provide some quantitative characterization for soft minima, solution uniqueness for group sparsity optimization problems, and finally some conclusion and ongoing research. So in many different areas of engineering and science, people just want to solve a linear equation, right? So suppose we have, they try to recover a signal X naught, but they make a lot of measurement, a lot of observation through Y naught. It means, over a node or a linear process, a random linear process 5, we can have Y naught, but we do not have X naught. The role of basically all we have to do is we need to solve this linear equation to get back the original signal X naught. The problem seems to be very simple like this one, but indeed it is a big challenge because the dimension is very different. The size of the observation M is much smaller than the dimension of our signal. But with some information, if we know some information about X naught, it is possible to recover exactly X naught. Now remember, in our linear equation right here, it is possible we have like infinitely many solutions. But we really want to get back, the only X naught we need. But if we know some information about X naught, there is a technique of optimization. They try to, model it in the following way. We minimize a cost function with a regularized chain knot, and the condition still a linear condition. So what are those regularizers? So for example, in complex sensing, signal processing, people want to have a sparse solution. Sparse solution, it means, we have like so many zero component in the solution, okay? And in that situation, the regularizer usually is the L1 function, L1 norm function. And what is the role of the D star, the linear function right here? Because sometimes the signal, maybe it is not sparse, but after some linear operation, it is sparse. So maybe X naught is not sparse, but D star X is sparse. And that is the reason why, we put the linear operators right here. But again, in general, it's just like a cost function Jx right here. And the constraint is a linear constraint. So in this paper, we focus in two classes of those kind of problem regularizers. The first one is for sparsities, we will talk about the L1 norm. For the group sparsity, that is L1, L2 norm, that the sum of many Euclidean norms right here, a Q group. And the last case is for low rank when we use the nuclear norm. The nuclear norm is the sum of singular values for the matrix. Okay, this promotes the low rank for the matrix. But in many situations, the observation we mentioned initially is Y naught. There is a phi X naught right here. It has some noise. Omega is the noise right here. It is possible for our observation. And in this case, the model is Y equals phi X naught plus omega. So for this one, it is not possible to recover exactly X naught. but people actually try to recover X naught in some sense. So the idea is we still consider optimization problems. Okay, but instead of the equality, they use the inequality, and it makes a lot of sense because you can see that phi x minus y right here represents for the noise, and the noise is very small. That makes the norm of that noise is more equal to delta. Okay, this is an inequality and a constraint optimization problems, and people have a lot of way to remove this constraint. For example, they can use Lagrange multiplier in this way with the least square function right here. Somehow those two problems are very equivalent. It depends on the parameter mu right here. It's not always equivalent, but for some particular mu they are equivalent. But if you can see that the problem phi right here, it is easier than the previous problem. Sorry, the baby is crying, but this problem 5 right here, the problem is easier to solve than problem 4. There's no constraint for this one, and part of the cost function, this linear function, a linear least square function, it is quadratic function. I'm sorry, it is completely differentiable, and of course we can take the derivative of this one easily. There's so many different algorithms to solve problem 5. Okay, but let's go back to the original question that if we solve problem 4 and problem 5, can we get back, X naught? All right, that is the point of this talk. The answer is yes, but it is the state of robust recovery. It's possible to do so. If you solve, you get the solution of problem 4, you get the or you can get the solution of problem 5. Then if delta is very small, the noise is so small, then that solution is very close to the original signal. So for this method, you will not have precisely X naught. You can recover exactly X naught, but you have something very close to X naught. That is the point. And there is a very famous result in this direction, established by Grassman et al. Just for the case of the L1 norm. So for L1 norm, they show the following: when X naught is a unit solution, if and only if the error between the solution to problem 4 and the original signal is a big O delta. And from now on, whenever we have this kind of error, we say it is a linear rate for robust recovery. And we also have, the error between X mu, that is the solution to the problem 5, the answer big O. Of course, mu right here need to be chosen as it is proportional to delta. Okay. This theorem, it looks very simple, but that is the whole Weber, they proved for the whole Weber. When we read this theorem, the biggest question for me is, why do we need unit solution? And I have like 2 reasons. They are very natural. The first thing is, look at the solution X delta right here. X delta is the solution of a tube optimization problem, and it is very natural. It's gonna converge to a solution of the original problems. You do not want that solution is different from X naught. You really want to recover exactly X naught, and that is the reason why X naught should be a unit solution for the original problems. Now the second reason they have right here is under some condition, when X naught is a unit solution for our convex L1 optimization problem, it is also a solution for L naught problems. We minimize, the norm 0 of X with the linear constraint right here. This norm 0, it is not convex at all. Solving it is NP-hard problems. So the idea is, if you can solve, you get a solution of convex problem with noise, you can recover the non-convex optimization like this one. So after this result, many people wonder what happened if the norm is not L1 norm anymore. How about the more general class? How about L1, L2 norm? How about nuclear norm? In this paper right here, there is a very pretty general result they established for any kind of norm. And the theorem say if J, our cost function is a norm, and it satisfies the red condition right here. I will explain this a little bit later, but they introduced the descent cone. So the descent cone TJ right here is a very simple cone. You can see that first they establish the level set right here, move this level set in the direction of X naught, and then take the convex cone. The condition they use right now is phi omega is bigger than alpha omega for any omega inside, the levels, the descent cone. And under this condition, we also have robust recovery with a linear rate. You can see there is delta, and here is the everything is explicit right here. So I draw a picture of just in the case of L1 norm. All right. So in L1 norm, the level set is nothing but the diamond right here, the L1 ball. Suppose X naught is this corner. We move it in the direction of X naught. We have this ball, and then we take the convex cone. So the pink areas right here, you can see it is the descent cone. Okay. Now we try to understand what does this mean. The red condition right here. This red condition, it just means that the kernel, the intersection between the kernel 5 and the descent cone equal to 0. But just for the case of L1 norm, all right, you can see this is a kernel, and this one is a descent cone. The intersection between them is trivial, and that is true. Okay. And but you do not see solution uniqueness in the previous result, right? I got to say it is hidden in that condition. In that condition right here, in the previous slide, I say it really means that the intersection between the kernel and the descent cone is a trivial, but it's not really like this one. Okay, the true thing is the intersection between the kernel and the closure of the descent cone is 0. Okay. But for the case of L1 norm optimization, or more general for polyhedral optimization problems, the descent cone is closed. So then you cannot see the difference between the descent cone and its closure, right? At the same time, solution uniqueness can be characterized by very similar condition, exactly the intersection between the kernel phi and the descent cone equal to 0. So the only difference between the red condition, this condition, and solution uniqueness is the closure of TJ. You can see that we have one direction definitely, right? This condition implies the second condition right here, but we do not have the opposite way. Okay, because the reason is the descent cone is not closed in general. It is for the case of L1 norm. It's not for more general case. And that is the reason why, for previous paper on L1 norm optimization problem, they only need solution uniqueness. Okay. For some other norm, especially those now not polyhedral, they need to have something more than polyhedral, more than solution uniqueness. Okay, but I also want to make an observation right here. What is the closure of the descent cone right here? The closure of the descent cone, it is the critical cone in optimization. And this critical cone is defined this way. DJ right here, it is just the subderivative, or in the case of convex optimization, it is the directional derivative of J. And it is smaller than or equal to 0, we're gonna have the critical cone, okay? Now let's consider the following very simple example for group sparsity. I have two groups right here. This one is, in L2, this one is just like in R2, this one is R1, right? And we also have a linear function, look like this one. For the example, the critical cone we have, we can, with some algebra, it's look like this one, all right? It look like this one. At the same time, the descent cone is the same thing, but without the boundary. So it is not this side without this side. So if you can choose the kernel function phi on this side, okay, then you will have that the intersection between the kernel phi and the descent cone is 0. But the intersection of the kernel phi and the critical cone is not 0, all right? The kernel phi is on this side, okay? What does this mean? It tells us that the difference between those two conditions, this condition and this condition are completely different. And as I mentioned, they are the same in the case of L1 optimization, but for other cases, they are different. So we have some initial questions to answer. I mean, now the first thing is, what does this mean? The red condition they have right there, the intersection between the kernel phi and the critical cone is trivial. What does this mean? And why do they, in the paper, they always need J to be a norm, okay? Thus J have to be a norm. And finally, can solution uniqueness sufficiently guarantee robust recovery with the linear rate? Now, I will try to answer those three questions through the talk. But for the first question right here, we make a very fast observation from optimization. It is very well known that this condition means sub-minima, okay? It is a bit surprise for us, the paper is very popular, but nobody recognized this one before. I mean, they always say this one is sufficient for solution uniqueness, but basically it means exactly sub-minima. And what is sub-minima? You can see the definition right here is very simple. Jx minus Jx naught. It is bigger than or equal to some common C, x minus x naught. This is some kind of error bound, right? You estimate the difference, the error between x to the solution by the cost function, Jx minus Jx naught. But the order right here is exactly 1. That is very simple definition of a sub-minima. Sub-minima indeed was introduced a long time ago by Polyak. He is the definition for more general case when you have like a function 5, extended real value function 5, and same definition, we have a sub-solution, sub-minimizer. If this inequality happens for all x in a small ball around x bar, okay? In the case phi is convex, this probably is global. It means you do not need the small ball around x bar anymore, okay? And sub-minima, long time ago, people proved that it's very important in many algorithms because it guarantees finite terminations. In many methods, not all methods, but many algorithms, you're gonna have like finite terminations because they have this property. From the sense of analysis, sub-minima can be characterized by first order information. If you use the sub-derivative right here, or the rational derivative for the convex case, the sub-derivative is bigger than 0 for any omega or w is different from 0, if and only if we have the sub-minimizer. So roughly speaking, I mean, if you can compute the sub-derivative right here, then you can get the characterization for sub-minima easily, okay? All right, so let me go back with the robust recovery. Before, I did mention that unit solution is really important for robust recovery. And this proposition will emphasize that idea one more time. So let me recall the original problems, I just want to remind that, you know, we try to minimize a cost function and we have a linear constraint like this one. So in this talk, we suppose that J is a continuous convex function. But in our, you know, but just for simplicity, you know, in our paper, we do not need convexity at all. All we need is the function J is continuous, and maybe it's Lipschitz continuous around the point question. Okay, but of course we also make some other assumption, but no convexity for sure. The proposition say S0 is unit solution even only if we have robust recovery. Okay, so you cannot distinguish solution unit from robust recovery. You can see that this one really means robust recovery. Any solution S delta converts to S0. Any solution S mu to problem 5 converts to S0. Okay, so you must have unit solution in robust recovery. Okay. This proposition is pretty simple, but it's very important in that sense. You cannot distinguish solution units out of robust recovery. And here is one of our main results in this section. If we know further information, for example, S0 is a sub-solution, okay, then we have the conversion, we have robust recovery with a linear rate. It means, you know, S delta, the arrow between S delta and S0, it is a big O of delta. Same thing for S mu. In this talk, I only write big O, but in the paper, we do establish a precise formula for the big O right here. Give full computation for big O. I mean, the theory looks very simple, but it covers like so many results in this area. And most results we know about linear rate for robust recovery. It is right here. It's right here. But you know, they use some kind of condition, many different conditions. Usually, you know, we can show later on that they are all equivalent, and they are equivalent to sub-minima, sub-solution right here. So but what is the new thing for this one? We do not need convexity, okay? If you read the paper, you can see that the cost function J right here does not need to be convex, right? So yeah, that is about the sub-minima for robust recovery. Okay, so now I want to recover the example 3. You know, we go back with the example 3. We try to minimize a cost function that is, you know, by using L1, L2 norm right here, norm 1, 2, very simple one right here. And then we make the following observation. You know, we estimate the cost, the different cost like Jx minus Jx0. S0 right here that we can show is a unit solution. And we recognize that this one, it is between those two guys. Okay. With the sub-minima, I want to remind you with the sub-minima, we need the order 1. But this one is order 2, right? Order 2 and S, when S is very close to S0, is much smaller than the order 1. It really means that S0, it is a unit solution, but it's definitely not a sub-minima. It is not a sub-solution at all. Okay. But the order 2 right here, it means it is strong solution. Okay. The difference between the sub-minima and strong minima is just the order right here. Sub-minima, you have order 1. Strong minima, you have order 2. But that is only a particular example. How about the more general case? We have okay, very nice theorem about this one. But before that, I just want to recall the definition of a strong solution. And as I mentioned, it's quite similar to sub-minima. The order right here need to be 2. Okay, and it can be characterized by second order analysis. This strong minima is also very important in algorithm, especially it guarantees linear conversion in many different algorithms. But here's a very nice result in our paper, and I really like it. Personally, we saw the following one. Any optimal solution to group sparsity optimization problems, when you have the norm 1, norm 2 right here, is unique if and only if it is strong solution. It is not a sub solution anymore. Unique solution is not sub solution anymore. Whenever the norm right here is non-polyhedral, it is not a sub solution. It is strong. Okay, but it's not just true for the previous problems. It is true for any group sparsity optimization problems. And after this thing, we recognize that maybe it is more natural to consider strong minima in structure optimization problem rather than sub-minima. So we want to look at how about the nuclear norm minimization problems, okay? We consider a very simple case like this one, right? We just like minimize the nuclear norm, and with a linear constraint right here, we have a very bad example after this one. Okay, we could have this kind of same problems, but only for the case of 2x2 matrix, linear condition right here. And for this example, we show that X0 100 is a unique solution. But if we choose X epsilon like this one, and we can check this X epsilon satisfy the constraint right here. However, you can see that we have under some algebra, the error right here is big O of epsilon cube. At the same time, the error between X epsilon and X naught is only epsilon, big O of epsilon. It really means that, for nuclear norm minimization problems, this unit solution is neither strong nor sub solution. The order raised to 3. Okay. But it's not only 3. We are working on this one, but the order for nuclear norm minimization is very tricky. It depends on the dimension we are talking about right here. Sometimes it could be 3, it could be 4, it could be any value. It's not just like 1 or 2. Okay, so we feel a little bit disappointed about strong minima for nuclear norm minimization. But recently, we have some nice result about strong minima. Now, a particular example of nuclear norm minimization is the following one. You minimize the nuclear norm again, okay, with the linear constraint. But this linear constraint is very particular. It is the product of 2 matrices. All right, so for here, this one is a linear operator, but this one, very specific one, right? M is a no matrix. M times X is the observation, why not? Okay, this problem, it is very important in multi-learning, multi-class learning, or multi-regression in statistics. So people show the following one. Very nice result that there is a unit solution for this one. And that unit solution is computed by this formula, right? And that's why here it is nothing but the Morvan-Ross matrix. Okay, this one is very similar to the case of least square optimization problems, right? But keep in mind, here is a nuclear norm. The nuclear norm is not differentiable at all, but its unit solution quite similar to what we know from the least square optimization problem. Okay, and recently we proved the following one. This one is not in our paper, it is in the common paper. But anyway, it really means that this solution right here is not only unit, but also strong. Okay. It is strong. It's not sub. Okay. So we have a lot of evidence about strong solution in L1, L2 in nuclear norm optimization. And that is the reason why we put a lot of effort to learn more about strong solution in those problems. But then we also wonder, so how about L1 optimization? For L1 optimization problem for basic pursuit, for example, right here, we already say many times that X0 is a unit solution, if and only if it is a sub solution. Okay, very strong solution. Of course, soft solution going to be strong solution. But we want to have something that is strong but not sharp. We look at lasso. Okay, lasso, you have quadratic terms right here plus the norm 1. And we make the following observation. X naught is a unit solution if and only if it is a strong solution for lasso. Okay. So strong solution is not just in, for the problem with non-polyhedral norm. It is also inside the problem with polyhedral norm, but not this one for lasso. It is unit solution if and only if it is strong solution. Okay, and this information allows us to recover a lot of result in long times established by many other authors, but I will not discuss much about this one in this paper. Okay, so the next thing is another main result of our in this part, that is the strong minima for robust recovery. We show the following one. If X naught is strong solution, we also have robust recovery. However, the rate is slower. Instead of rate delta to the power of 1, we only have the rate delta to the power of 1/2. And this rate seems to be very new. I mean, for the first time maybe in robust recovery. And we also have a very nice result right here. You can see that for group sparsity or even nuclear non-minimization, the special class. Robust recovery, we have robust recovery with the rates only big O delta to the power of 1/2. Okay. If and only if the solution unit occurs. Okay. So I want to say that unit solution implies robust recovery, and the rate is big O delta to the power of 1/2. So for different class, especially for group sparsity and nuclear normalization. All right, so the next part of my talk, it is about quantitative characterization for subminima. So let me revisit the case of L1 optimization problems when people try to minimize L1 norm with a linear constraint right here. Solution uniqueness can be characterized like via many different conditions. I cannot list them all right here because there's so many. If you know about this area, you're gonna so many different conditions for this kind of properties in L1 optimization. I only have like list two conditions right here. The first one is the non-space properties, and the second one is the non-degenerate source condition. They are equivalent in some sense. Roughly speaking, we can say this, the first condition right here is the primal condition. The second condition right here is the dual condition. Okay, they are very nice, but it's pretty hard to check them numerically. You can see that the first condition, it happened for all V in the kernel. The second condition, you need to find some Y in this set such that this inequality happens. Okay. And I will try to tell you how to check this one numerically later on. But after those two conditions, a lot of Weber try to generalize them for the case of non-polyhedral norm. Okay, but they only have sufficient condition. Only have sufficient condition, and we also wonder what happens. Do we have similar characterization for solution uniqueness when J is not polyhedral? The quick answer is it is possible, but it's not trivial. Okay. Now in this talk, I will focus on the case of decomposable norm. In our paper, we consider the function J right here. It could be any convex function. All right. Non-convex function for robust recovery, but when we go to subminima, we suppose that the function J right here is convex. But for the talk, for simplicity again, I consider the case of decomposable norms. So decomposable norms really means that we can decompose the subdifferential in this way. The projection to a subspace T is just a unit vector E, but the projection to its T orthogonal T is with a dual norm is more equal to 1 right here. Okay. So in the case of norm 1, you can recognize that it is very simple. This unit vector E is nothing but the sign of UI. I is the active set, right? And IC right here is the complement of I. T is the subspace Ri times 0K. And as I mentioned, the decomposable norm includes L1 norm, L1, L2 norm, and nuclear norm. So it covers 3-man class I want to talk today. So here is the very first theorem in our in this direction. We establish the characterization for sub-solution. Now, S0 is a sub-solution if and only if the restricted injectivity holds and the non-deceleration source condition holds. So this condition is quite similar to what people have with the restricted injectivity for L1 norm. This one is also quite similar, okay? Quite similar. There is V in the relative interiors of the subdifferential, such that dV is in the image of phi electron. Okay. So the equivalence right here, we give some new information. This problem condition 2, all right? This condition 2, I just want to recall that it's quite similar to this condition, okay? It is not just sufficient for unit solution, okay? But it is a characterization for subminima. There is another information in this theorem that we provide a more quantitative, a condition that can be computed directly to check this kind of condition. Based on what we call source identity. And source identity is the optimal value for these optimization problems. Okay, very simple optimization problems. And with the new information about the operator N is the matrix such that the image of N star equals the kernel of 5. Okay. So all we have to do is the restricted injectivity, somehow is very interesting. Most of the time it is trivial. It occurs. Okay. So all we have to do is we check this identity, measure this identity is small and equal to is strictly smaller than 1, based on solving this convex optimization problem. All right, so here I just want to mention a little bit about how to compute the source identity. So again, the optimization problem, we want to solve it right here. Okay, the information first is about N. So how can we compute N? How can we find N? So N can be chosen from the singular value decomposition of 5 because the information we have right here is image of N star equals the kernel of 5. Okay, so N, we can find it from basically from V star right here. Okay, we get the information N from the V star right here. And this problem is a convex problem. We can use some available package to solve it. In the paper, we use the CVX optimization package to solve it. Especially for the case of a group sparsity right here, you can see we translate this problem into the following problems. The minima T, same linear condition, but we add, instead of using the dual norm right here, we write it in the constraint. That is, the Euclidean norm squared minus T small equal to 0. Okay, so this problem is not just convex problem, but it is a second order cone. This constraint, it is second order cone programming, and we can use some package to solve it easily to check whether or not rho E right here is smaller than 1. For the low rank case, J naught U equals the nuclear norm right here. This optimization problem can be translated into a semi-definite programming with this semi-definite programming constraint right here. Okay, and of course, again, we can use convex optimization to solve it. Okay, but of course, I mentioned that it's possible to compute rho E right here, but there is a faster way to check the condition. We have a very nice estimate for rho E. So rho E is more than gamma E. So we have this identity. And this gamma E, what does this mean? This gamma E is the dual norm of a solution to this problem, right? For rho E, we need to find the minimizer, the optimal value. For gamma E, tau E, for tau E, we just need to take a solution of this one. And that solution can be computed by using Moore-Penrose inverse matrix S squared. Okay. In the case of norm 1, this identity was appear in this paper. All right, so how can we check a subminima wisely? Now, first we're gonna check restricted injectivity, and then we do not go directly to rho E, because rho E is we got to solve an optimization problem. Instead of doing so, we check this tau E. If this tau E is far away from 1, it's much more than 1, and definitely S0 is a subminima. Okay, if this one is near to 1, let's say the 0.99, you may have some error in your computation, right? You are not sure about S0 is subminima or not, then at this moment, you try to check the rho E right here, okay? Usually rho E is gonna be far away from 1 if it is subminima. All right, so I think I have maybe 5 more minutes. We talk in this session, we talk about the group sparsity. We consider group sparsity with the L1, L2 norm right here with the linear constraint, and we can establish a very similar result, but it is much more complicated. Okay, so here we establish the characterization for unit solution of group sparsity problems. But this one, again, it means the strong solution. And then we got to use second order analysis, second order variational analysis to establish this characterization. Now, we introduced 2 definitions, strong restricted injectivity and analysis strong source condition. Quite similar to the case of subminima, but we had an extra term right here, that is epsilon. E, right? The set E right here, it is quite different from the previous one. We need the extra terms right here. It's not just the kernel phi intersection with the kernel right here equal to 0, but the extra terms. And this E, set E, that is a subspace, is established like this one. All right, we can compute this one directly, and the analysis strong source condition is also very similar to the source condition, but instead of using the matrix M, and we got to use the matrix M, and the difference is the image of M star is the kernel of phi intersection with the set E right here. So roughly speaking, the difference between subminima and strong minima, it is extra set. Okay, and after this one, we also try to establish the idea how to compute the strong source condition. We do the same way. We use second order cone to solve it. We also have an upper bound for zeta E, that is gamma E, and again, usually we check gamma E right here. Gamma E, compute gamma E is much easier than finding zeta E right here. If gamma E is much more than 1, then S0 is strong minima. If it is close to 1, then we use ZE to check it. So we run some numerical methods. We test only, we make only 100 tests, but it's possible we can make 1,000 tests or even more easily. We run like many random tests for 5. Okay, 5 is a random matrix, and we recognize that X naught, we solve that problems, right? We get X naught, and X naught is a solution. We test the restricted injectivity, and as I mentioned, surprisingly, it always happens. Okay, but then we look at tau e, and tau is smaller than 0.99. Okay, smaller than 1, then we have sub-minima. In this case, we only have 11 cases. Okay, but when, so the other case, 89 cases, right? But then we test rho E. Okay, rho E gives us a loss of case. That is 60 case, rho is more than 0.95. But rho is right here, the arrow is very big because that is, you solve and we need to put the arrows a little bit bigger because that is solving an optimization problems. So we have 60 cases like this one. Okay, between 0.95 and 1.05, we have 29 cases. For those 29 cases, we try to find gamma E. Gamma is more than 0.95. Gamma is, we have the explicit formula, easy to compute. We have 26 cases. Okay, for the case, if gamma is bigger than 0.99, we only have 3 cases. And for those 3 cases, we test with zeta E. So you rarely use zeta E right here, but still, zeta E, we're gonna give you like 3 strong solutions. So through our test, we recognize the following information. We have 91, we have 91 sub-solution, we have 29 strong solution. It really means that all of them are unit solution. Okay, why is this? This is belong to the area of exact recovery with high probability, right? So with high probability, we have a unit solution. And for exact recovery, people usually use sub-minima. They do not mention about sub-minima in the papers, but as we mentioned already, sub-minima is hidden, it's behind a lot of result in this area. So here is some conclusion. In this work, we show that sub-strong unit minimizer, very important in robust recovery, even we do not have convexity. We can establish quantitative characterization for sub-minima and strong minima as well. And there is a lot of further information in our paper. It's a very long paper, 43 or 45 pages. We are also working on some open questions. Now, the first thing is we try to deal with nuclear norm. And we recognize that nuclear norm is much more complicated, especially the strong minima. The second order of the nuclear norm is much more. The first order is very simple. Everybody knows how to find the subdifferential of the nuclear norm. But for the second order, it's very hard to understand it. So we are working on this one. And there is one more thing. It's very interesting. The question is, what happens if we do not have solution uniqueness for robust recovery? Of course, you will not have robust recovery, but you're gonna have something like this one. You can replace the solution of X naught by the solution set. We already have some result in this direction, but we keep working on this one. The final thing is how to use strong minima in exact recovery. Sub-minima is hidden in a vast area of exact recovery. Nothing have been done by using strong minima. So we believe that this is a big area, for us to work on. And that is everything for my talk. Thank you so much for your attention.